Hey everybody, here we are as promised. I know some people are going, so what? I'm not going to watch anyway. But of course, you wouldn't be watching if you weren't, if you can hear me say this. But again, this is going to be, these are recorded and you can go back. So we are now going live to our our two places, which is Facebook, our webpage for Principia Mathematica 2, and we are also going to our new YouTube channel, which is Principia Mathematica 2. So you can either look them up or we can put up let's see here, we can put up the information for you to go and find that. So here's one. If you go to youtube.principiamathematica2.com, that will take you to our YouTube page, and we would appreciate it if you hit the subscribe button for that. You'll be notified because we are now live to YouTube and Facebook. Also, if you want to go to our Facebook page, if you prefer interacting even with us on Facebook and watching us live on Facebook, you can do so, and we have these special links that'll get you there. This is facebook.principal. I can't speak. I can't edit these. These are live, folks. Usually with my videos, I edit them. So facebook.principiamathematica2.com, and that will take you to our Facebook page. And a reminder, too, that I am with my father, the Particle Guru, and say hello.
Hey, guys.
And you can go to his webpage. He's got, how many videos do you have now?
126.
126. He has them exactly counted, and his subscribership is going up. But if you haven't subscribed, support my father. I mean, how many 82-year-olds?
Almost 83.
How many almost 83-year-olds have a YouTube channel talking about physics and a new model for the universe, the entire universe? Perhaps the first one of its kind. Well, we think so. Anyways, you can go ahead and subscribe to him if you can. And of course, I'm also got my YouTube channel, youtube.dissidentscience.com. That's a more general one, so it's not specifically about the particle model, but it talks about science from a dissidence point of view. So anyways, I want to welcome everybody, and we do have our comments open, so if you want to say hello, just say hello. Say, type in, I'm watching you. We can see with people watching, actually, with counts. And today we're going to talk about what we did today on our very first day. Today is July 3rd. I'm off on a holiday, a paid holiday. My dad is permanently on holiday since his retirement. And so this is no different. And you notice the spots here. That's because the window's right there, and we're getting G1 particles coming in waves on my face. So that's pretty cool. You can see, but that kind of goes away depending on the cloud coverage.
Those are G1s.
They're not going to know that until they read our book. But anyways, we're going to talk about what we did today. And I guess I will start off. I spent 2.5 hours in the morning fighting with Microsoft trying to get an email fix for our science society, and I did not do that, and it was very frustrating. But today I did succeed in doing 2 new graphics and updating at least 2 or 3 others. And I'm going to show my father those, but you're not going to see them because they're going to be in the book. And people are asking about how do I get the book? Well, we will have on our website soon a place where you can purchase it ahead of time for our very first printing. I think we're going to probably maybe get 50. We can spring ourselves to buy 50 of them, and then we're going to have to sign them. That's the hard part.
Yes. Do I get a rubber stamp with my signature on it?
Well, I'm going to sign them for sure. Yeah, if you're going to get the rubber stamp from my father, it's going to go down the volume because he's really it's because of him. This whole thing. No, it's not true. It's both of us competing, putting it together. Also, I did record something. So those of you who do subscribe to the YouTube channel, especially the YouTube channel, I already have been I'm putting up recordings of some of our banters during the day. So instead of when I go into my father's suite, I guess you call it. It's his bedroom, office, laboratory,
without a beer refrigerator or a hot plate.
Well, actually, we have one, Dad. We've asked you if you wanted one, but we have also a fridge in the regular kitchen. But anyways, I'll go over there at times, and we sit down and we talk. Well, I have now forced ourselves that any of these discussions are going to be recorded, and I record them to YouTube on an unlisted YouTube playlist. And if you subscribe to us, I will let you know where those are, because I will put a message in the community on YouTube, which only goes to those who subscribe. So if you want to see videos of my dad, the first one is us arguing, right, about the origin of the G2. That was pretty good. It's like
the source.
My dad, yeah, where they come from, and my dad would argue about that. Of course, we're not going to tell you anything about it, but it was really interesting because you'll see two people who are actually very. We are the authors of the TPM, the particle model, but we have disagreements because we're still hacking the universe, and it's interesting because sometimes there are really boisterous interchanges, and those interchanges, I remember just a day ago, my wife Doris, she was like, and my daughter Luanda going, how you guys? They thought we were just gonna break up and Dad was gonna move out and everything. It was just one of our discussions. So, anyways, if you subscribe to our YouTube channel, and let me put that up there because I have the wrong one up there. But if you subscribe, let's see here. Oops, hello. That's us saying hello to you guys. So if you have your comments, we can put them up and say hello. So please, again, say hello. Let me put up the YouTube. There we go. So please subscribe. Bring up the subscription level for our channel for the book, and you will get some videos that no one else will get. And in the future, that will, again, they will not be public. All right, well, let me tell you about what I did, and I'm not going to show you. Oh, man, what am I even watching this channel, Dave, if you're not going to show me? But I'm going to show my dad so you can get the reaction. Of course, it's going to put, as they say, agua na sua boca. That's what we say in Portuguese, in Brazil. See my shirt? São João? No. São Jorge.
Sit up straight.
São Jorge. So anyways, I'm going to show him, Dad. So anyways, one of the questions we got on the YouTube, on Facebook, from one of my friends, actually Brazilian friends, Jose Zé. He actually, we knew, my wife knew him in Brazil when we lived in Brazil. He's a mountain climber. And he asked, well, I don't, I've got math 3. I think it was just, the way they said Portuguese. I got low-level math, elementary school math. Can I understand this book? Can we understand this model? The answer is absolutely true. And I'm going to give you, if you didn't go to our website, which is going at the bottom there, you can see the website, principiamathematica2.com. If you go to the website, you can read this. It's in the forward, but I'm going to read that for you today. And it's by Robert Berger, a good friend who was there when this whole book really, and this whole particle model really got started. It was on June 23rd, 2015, really, when this happened. But he wrote a forward for us, and he wrote this one part about the simplicity, which I thought was really good. So I'm going to read it for you. Here it is, and I quote from Robert Berger. Probably the biggest threat to the theory is its simplicity. Intellectuals like to show off by claiming to understand the most bizarre and complex scientific theories, and when the theory can be understood by a regular educated guy, it threatens their status and even their academic and or professional achievements. I hope the scientific community will embrace this theory and work to solve unanswered questions. And with any specific breakthrough, there always are those who question it and present evidence to support their point of view. This is healthy, and as long as the intention is to open rather than to close the debate. So I'm going to read that last sentence there. This is healthy as long as the intention is to open rather than close the debate. So I think that was really interesting. First sentence there is really a doozy. Probably the biggest threat to this to the theory is its simplicity. So we expect people to say that because the experts want it to be complicated. And of course, it's complicated and not intelligible because guess what? It's illogical, so no one can understand it. They just pretend to understand it. That's our opinion and many other people's opinion. So anyways, that's a quote and answering one of the questions we had from one of our people here. And Farouk, he says, hello. Hello, Farouk.
Hey,
we know him. He actually he's waiting for our book. He's one of the 2 people. I'm kidding. We actually have a lot of interest in the book.
He made a good comment in my in my on my page, my particle guru.
Okay, okay.
Yeah, it was very nice. I thank you for Farouk.
So anyways, it's really nice to see you here, and we're going to talk today about what I've done. So I'm going to show my dad on this other. We have a screen here where we can see ourselves and watch what's going on with our control room here with StreamYard, which streams it live. And on the other one, we have our book, which is written in overleaf.com. It's an online text processing from latex online, and so we're using that. And so I've compiled the latest version to show my dad the new graphics. He's going to go oohs and ahs. So I'm scrolling here, and come on, is it going to like bring it up or not? Uh-oh, I hope we don't lose it. But anyways,
You know, Dave, if you expand it,
oh, okay.
I find that you don't lose it so easily. It stays with you better.
Okay. So, anyways, this one which is the, of course, the four. This one's actually on the internet on our website, which are the four movements, the four classifications of movements. This one you already know, which you liked. Here's my new one. Look at this. You can see a earth here with a tree and an apple, and these are all the intuitions that we claim that these intuitions allow you to hack the universe using the rules of our model, the particle model, including falling objects, collisions, curved paths, orbits, and complex paths. And these complex paths, and these I made a really nice graphic for that. So pretty cool. See there?
Yeah.
Pretty nice.
I see you got the corona around the sun.
No, that's just my way of making the sun, which is to say it's his bullet. Oh man, it's a good thing that I'm the artist and not him, because
Well, they've seen those who watch mine. They've seen my artistry.
that'll get him to your channel, Dad. Go sell it there. Go sell it.
Hey,
No, hey, I love his stuff. His stuff is very good. Okay, let's keep going. We're going to get to Dad because we have an interesting discussion that we had the other day, and we're going to continue. Now, instead of the levels of the universe, I'm going to show you this, and I don't want to give it away, so I don't want you say anything. I'm just going to show it to you. All right, but this is the new things, and I want you to look at that. See that?
Yeah.
See that?
Yeah.
Pretty neat, huh? So we get away from the labeling of the G1, G2, and all these levels. This is just talking about this concept.
You have it at the bottom, but there's probably no other way to do it.
Well, what I'm saying is this is the change. We're not going to, okay, and I thought that really works well. And this one is actually from Borkert. Borkert, one of the people who our model's based off of. We've got his graphic from the cover of his book, Universal Cycle Theory.
Yeah.
Oh, and actually I spelled universal wrong in the graphic, so that's an thing. Okay?
So I won't make my comment.
Good. Yeah, not making the comment. No. He's not making the
I
comment.
wanted to make the comment.
Nope, you cannot. We're going to talk about that later. So I'm going to show you. That one, of course, is in there. But here is the other one I've just put in. And I added some text to it. So this is in the particle flow area about electricity. And there's the new graphic there, redone. And you can see this comet going through and this kind of structures of suns. And I even put a little G2 field. Remember I was talking about doing that? So that reminds me. And of course, if you don't have to put it everywhere, people can get the analogy for it. But this is a visualization of electricity using suns and comets. And that's it's not only a perfect visualization, but it's a perfect, it's the way the mechanism really works in our model. So that is pretty cool. So those were the graphics I've worked on. I even put in some of the stuff here and talked about fractals. And so how did you like that? He doesn't know. Okay.
Yep.
Anyways, did you want to make a comment about that other one, or is the particles one, or is that something we can talk about without revealing too much? Or
No, well, I just want to make a general statement about what is a particle at a level versus what is an atom and so on. what the real definition, and you've got
Lots of
normally
difference.
we think of particles in level one. N1 and G1 are each individual particles, but in fact they're not. They're made up of subatomic atoms, which again is another set of particles.
So what are you saying?
So no, the question is, in any level, what is a particle? And I think you're giving the examples at those levels. As what is a particle? How do you define it?
Right,
And you're doing it visually.
Right, and so this graphic that I did, which is a new graphic, which is showing you levels of the universe, and we call them all particles. Doesn't matter the size of them, because particles are made of parts, right? And the thing is, a lot of times, I think maybe what you're trying to say in the beginning was like particles. We'll think of like subatomic particles. Oh, those are particles, but we're not going to think of a sun as a particle, when in reality it is. So that's what this graphic's about. So anyways, I think I got some really good stuff done for the day. Really only working a half a day because I lost some time. Let's see, we have Greg Nicholas. Does light slow sound down? I don't know. That's a question. Does light slow sound down?
Theoretically, yeah, it can, but practically speaking, in such a short distance, you probably couldn't even detect it.
Yeah, I think with our model, if you look at it, light are G1 particles coming in waves. It's not a wave in a medium. That's the big difference between us and ether. And light is G1 particles, which is also gravity. And if that's coming at something, you're coming at atoms. Atoms are has nucleuses. And the G1 particles, which are gravity and light, which are the same thing because they both travel at the speed of light, and we measured them coming to us at the same time. If you have the G1 particles hitting atomic or molecules that are nucleons with G1 particles going around in clouds, just like electron clouds, light in reality is just not a really strong force, believe it or not.
But back to his question. Let's suppose that you have a huge number of floodlights just with watts and watts and lots and lots of power, and you have a weak sound signal. Could that have an effect?
Well, you have to know more about sound, which I'm not an expert in, right?
Well, the sound wave is made out of atmospheric particles, oxygen, nitrogen, and miscible. So it's normal level 1 atoms, and light is G2.
No, it's not.
Excuse me, G1, thank you. It's G1 particles which act gravitationally on those, which would push. Now the question is, can you push enough of these? Like, take a lot of laser lights, really high power laser lights, real strong, pushing against those atoms and molecules in the air. Seems like I know I'm going to extreme.
Well, I think first of all, I think the answer really is we're not experts at how sound goes through molecules in the air. So let's say just take some simple ideas that light. A lot of light will heat things up. So if it's heating, heat was really just making the nucleuses of atoms move more. Does that affect sound? And if it does, how does it affect sound? So I'm not sure what the question is about. I mean, maybe you could clarify why you're asking that, because our model, it's not something that we look at really, because we don't talk about sound. It's just not something in the physics world that we're trying to solve. But
I mentioned it's mentioned in the book, but it basically says we accept the standard explanations.
Yeah. We have to. Our model will do that. So explain that. Okay, so that's what I did. I did two new graphics, and I redid a number of them, sort of getting them in line. And I've been going through, and I actually wrote something on the part of electricity. So now, what did you do, Dad, for your?
I turned off my phone.
Okay. So what did you do today for the book? Well, you're doing it every day almost.
Yeah. Well, Well, there's several things I did. I mean, to make a simple statement, I finally put something in on the electroscope.
Okay.
Okay, it's not much. There's one graphic, and some words explaining. But the interesting thing about the electroscope, and I ran
Well, can you
into
tell
this.
people what that? Can you tell? I mean, I would imagine 99.9% of the people watching don't even know what that is.
Well, an electroscope is a simple device that has a top where you bring a charged rod, negatively or positive charged rod, and a simple one has two gold leaves that are together, and when you charge it up they separate, and depending on how much you charge it a little, it separates a little.
Right.
An electroscope has got a little bit of addition. One of the legs is fixed, the other one bends, and it has a scale, but it's scaled, but there is no
Okay.
standard for it, so there's no units of charge, like there's not coulombs.
Right.
But I tried to get this resolved really early, and I had a hard time with that. When I was explaining it to Dave, this was probably back in 1916, 2016, whatever year. You know, a lot,
2016.
really early in
Yeah,
our,
it was a
in our work.
one year after. we
And,
saw it,
and
yeah.
Dave said, well, have you thought about magnetic field? That's about, and that's in the book. It explains it based on the fact that the G1s from the charged rod actually flow into the electroscope, causing a flow of G1s through it, causing an electric field around each one,
Which
and
are
it's in the
G1
same
particles.
direction
It creates orbits of G1 particles, right?
around that. And since they're going in the same direction, the magnetic fields actually oppose,
Right.
and that pushes them apart through collision.
Yay! Because I've been getting my dad to remember about magnetism, and again we have random particle fields. That's gravity. We have particles that go around in circles. That is magnetism. And we also have electricity, which is just particles flowing really in one direction, not coming back, and it's sort of guided, pretty intense. And then we have light, which is basically particles coming to you in waves of particles, like brum, 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 coming at you. So those are the things. So we look at it. Well, that's cool. That's actually pretty good. I'm pretty happy because that was a.
It's a short section. It is, and that's after I've gone through the pith ball.
So I'm going to have to
already.
make that. That'll be a graphic, right?
Yeah, yeah. Well, and
Or
then
we'll use your
the
graphic.
other thing I did was this is an interesting one that I actually wrote in the book, but I think I'll take it back out because I worked on it since to actually see if you could do this practically.
Mm-hmm.
And it turns out I don't think I could develop the equations, but here's the principle, very interesting principle. So let's assume we have an infinite universe that's static. By static, I mean it's not expanding and it's not contracting. It's a static
right.
universe, an infinite
yeah.
static universe.
Mhm.
What does that mean? It means the stars aren't moving away
Mhm.
in general. I mean, everything moves a little bit. Andromeda's coming right at us, things like that. But basically, the stars aren't moving away and coming real close necessarily. But then you have redshift. Okay, the explanation we have in our book about redshift is that the drag caused by G2, the G2 gravity, slows the light down. So it's emitted from the star, and it's got a certain wavelength. That wavelength stays the same, but that drag causes all the particles to slow down. So they're
Wavelength
moving
gets smaller.
fast, and then they're moving slow. But that can cause redshift.
Mhm.
Okay? Now, what I thought of was if you measure the redshift for a given star,
Mhm.
and you know what the and you know the distance, because you can they can get the distance of the star through triangulation. You know the distance, and you know how far it has to travel, and you got the redshift, so you know how much slower it's going. Can you develop an equation for drag, which is proportional to the speed difference of light versus the G2?
Mm-hmm.
Can you develop a formula for drag, use the numbers of redshift, use the distances, and calculate the speed of the G2?
Ooh, that's really interesting. That's really interesting. So,
I got to turn.
yeah, you have to turn it off. Just turn off
they're
your
always
phone.
calling me with junk calls. And I
Right, but
don't.
you need to turn it off. See, my dad's not used to being on live stuff. He has all his is on tape. So, anyways, that's very interesting. So electrostatic, which is again, it's sort of like you make static electricity and things like the static gets in the apparatus and makes them separate, and then you take away the static electric charge and it goes together. Things like that.
Except it isn't static electric charge.
I know. I'm telling people what it is, what they are used to.
Yes,
But
know.
no, there's no charge. Charge is a magical thing. You can't just take this thing and say, I'm going to put a plus on this, and I'm going to take my mouse and put a minus, and because I put the plus and minus, they're going to come together. It's absurd, and that's one of the things our model will tell you why they move together for reasons. So. Okay, so you did those two. What else?
Well, so later on this afternoon, I actually drew drawings of it, tried to develop preliminary equations, and there's a couple of problems with it. Number one, there's only one situation. There's the sun, the earth, and the star. There's only one configuration. What you need is more because turns out there's more unknowns. It isn't just the speed
Right.
of the G2 that's unknown, it's the force applied that's unknown.
So basically in a sort of a top level down for people, this is maybe too technical for you, is that one of the things about light is people in light right now, if you ask the average physicist or person who will, or look it up, light, when you shine it out there, like you take a flashlight or a laser and you shoot it out into the universe, it will continue at speed c and never stop and continue there without ever slowing down. That's an ideal idea, and it isn't true. And one of the reasons we think people say there's a Big Bang is that when things move away, remember, this is how I would talk to you about it. Why do people say there's a Big Bang? Well, they say there's redshift. What is redshift? It's like the Doppler effect. When you hear a siren go by, neener, 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 it goes down. The frequency changes because its speed is moving, and so that the sound waves, the frequency that they're coming to you, actually change because of the speed of the source of the sound. Well, the same thing, the idea that they saw, that is, these stars are supposed to be this color, but they're more to the red side. If they're more to the red side, they're shifting because why? Like the Doppler effect. Therefore they are moving away from us, and wherever we look, they're moving away. So the universe is expanding. And then they have other reasons they say. But that's why we're discussing this, because many of us, and not only our model, but it's called the tired light model, which is light is really something. It's not nothing, and it doesn't go through an empty space. There's stuff out there because it's very small. You can't see it, but there is stuff out there, including the light particles themselves, gravity particles, which are the same in our model. And when they go through space, they don't go through space as if there's nothing there. There is stuff there. So that what he's talking about, the drag and trying to calculate all those things, the light particles, which are in our model G1 particles, those things are flying through the universe, and they're encountering another field of a lot smaller, much faster particles that are all there too, and that causes it. So that's what he's talking about on those calculations for those people.
But on the other hand, I have the older calculation that I did, what we talked about before. So there is an estimate in the book about what it is, but it's an order of magnitude about 30.
Okay.
It's almost c squared, but down by a factor of 30.
Okay.
Less than c squared by a factor of 30. That's based on some assumptions I make, putting it together to show what it might be. Fact is, we don't know what the speed of the G2 is.
But let me say this, because my dad's talking in very technical terms about all this stuff, and what we're saying that is for the G1 particle going at the speed of c. The reason it's going at the speed of c because there's a smaller particle down another level, even smaller, that goes way faster than c. So one of the technical possibilities would be is that in our model we know that that is going faster than the speed of light. It has to in our model. And if this model is correct and people start applying it to the real world and trying to figure out how to release these, if they can release them in waves, I have done calculations, and that means you could communicate to Mars at about a fourth of a second. Now that's really fast. And that certainly would be really interesting to do. But again, technically, we don't know, how to do that. We don't even claim to know. But our particle model, being real physicality of really real things for everything, the idea is that, as Dr. Carazani, my mentor in all of this, he said to me, it's just a matter of time that the technical aspect, engineers will hack that in some way. So that's pretty cool. All right, and so that's what you did today. That's a lot already.
Well, I also worked on the Wang thing.
Oh, that's right. And the Wang eclipse is the one we talked about that in one of our videos, right?
Well, I've talked about it.
Right.
I wrote a paper on it back in 2012.
Basically, there's a guy in China that measured during the full eclipse a bump in gravity. The gravity, there's a bump. The Allais anomaly, also a guy in France, also measured that or showed that pendulums, just regular pendulums swinging away, went all nutso at the beginning of a full eclipse and then went nutso at the end of the eclipse and then came back to normal
That's
swinging.
the amazing part. After all that motion, random as it does look, it actually comes back to its normal position. And I don't know how close, but they actually show it on a graph how the line goes. It would normally go this way.
Did other people do this to verify it?
Oh, there's been numbers of tests
Okay.
done. Yeah.
Okay.
But these are all tough to verify, and the biggest reason in my mind, is that there is no eclipse that's exactly the same.
Mm-hmm.
And you're not in the same place on the Earth when it happens.
Well, plus it could be because of the it's not perfect. They're not perfect spheres. They're not perfect anything, right?
Oh, yeah.
That there's all kinds of variables. There's wind. There's all kinds of stuff. So,
But there are similarities in terms of the answers. People got similar, partial answers that were similar to Wang, partial answers that were similar to Allais, but nobody's ever been able to actually duplicate those curves that are
again, we're talking very specifics that he and I will understand. But the Wang eclipse data basically shows that at the same time we see the eclipse happening, there are variations in gravity, and that means they both arrive here in the 8 to 9 minutes it takes for a light to get from the sun. And if you really look it up, the speed of gravity, I've read in numerous places over the years that the speed of gravity in the standard model, and there's no model, but in their standard way of they think things work in the universe, is that in fact that it goes at c. So so you're working on that. We had that in the appendix.
The question is, where do I put it?
Right.
And I have a suggestion.
Okay. We're talking about the book now, The Wang Eclipse, which shows us that light and gravity come at the same time, and that during eclipse the light is affected sort of as a gravity. So
what I think our readers would like is just the explanation of what happened. What happens to the pendulum, to understand what happened.
Mm-hmm.
I think they would like to understand what happened in the Wang anomaly or Wang, so they get an idea of what's going on without giving the answer. We put this somewhere in the main part of the book, but to explain in detail using the particle model to explain the pendulum is particularly hard. Wang eclipses not as hard. Put those in the appendix.
Mm.
Put the detail. Normally, what we normally hack is in in part 3.
Right.
But now I'm saying hack them only, but you get them interested
Sure.
first. Okay.
Sure. So in the appendix, much more detailed, maybe even some equations kind of stuff. Huh?
Well,
No, I'm not saying for the Wang, but anyways.
probably
So
not.
saying, talking about putting it in this is what's happening. This is how it's working in the universe. These are the
So-
particles that are moving, and this is why it happens. And then having a much more detailed information, maybe in an appendix. So that's what you're saying.
Well, that's what as initial start. So
Right.
if I'm going to continue working on it tomorrow, I want to know. I'd like to at least have a preliminary agreement. Right now, I have it after gravity and light because they have just now understood both. Read about gravity and light. Now here, I call the section anomalies, and I explain what an anomaly is, and then I go into Allais, his 2 anomalies, and then Wang, and then you can also bring in the correlation to Eddington
Yeah, the small reference. Yeah.
at the end,
Right.
just at the end.
Okay, well, Greg Nicholas, who's asking about the slowing down, does light slow sound down? He says, I am right in thinking that light has mass. Yes, it does. And therefore, the mass of G2 is less, making it quicker than C. Yes, but it's not because it's less mass. It's just the way. For us to have a particle called G1, which is gravity and light and electricity and magnetism, the same thing, because they all travel at the speed of C. That's one of the things that I added to this model, because my contention is that how can you have particles all moving or wanting to be moving around the speed of C and have them different particles? How would that work, right? Is there a speed limit? So the big ones, you'd have to put more energy into them. So the idea is that if we know in the Wang eclipse that light and gravity are coming at the same speed, even the standard model talks about light at the same speed as gravity, and we also know that electricity is traveling near the speed of light, and that actually magnetism in particle accelerators, which they use for particle accelerators, gets them close to the speed of light, then that's also moving at c. Well, they're going to be the same particle, but for that G1 particle to be moving at c, it's going to need something with impedance below it that keeps it going. So if you move it out in space, it's going to keep going. Well, that is going to be G2, and it's going to have to be going way faster than the speed of light.
Let me go ahead and answer a question a little bit differently. Yes, all objects that are built up of particles or subatomic atoms are built up to something, they all have mass in the sense that gravity can interact and push them. And what's pushing has mass, and what they're pushing on has mass. Now, it's not the same mass. A light is a particle that, in our model, that's a G1. You can't, in our model, you cannot measure the G1 particle with G1 gravity, because G1s collide. That's all they do is collide. That's not gravity, that's collision. So G1s are not measured in kilograms, even in spite of what in our model it isn't. Now, regular science has correlated with the energy. I lost the term, but it's either in energy or kilograms or grams, and there's a correlation between force equals mass times acceleration and the electro force that they measure it with. They measure it with the right. This is amazing. There's a video I did in the particle model about measuring the mass of the electron. You should watch that, because there's a video that I can reference in that. I did reference in that you can watch and see how this experiment goes. And they actually use voltage, and they use a magnetic field to accelerate the electrons in a precise circle. They keep adjusting this thing until it's a precise circle, and through equations, they end up measuring it. Now they're measuring it correctly because the voltage is G1 particles moving, and magnetic field is G1, and those things are moving because of the F2 force, gravity 2. Okay, and gravity, you can measure the G1 particle with G2 gravity, level 2 gravity.
And what would we call that? What kind of force?
There is no name for it.
You know what I keep telling my dad, because he said I make it the Hilster force or the Hilster force, and he says we can't do that. It's too pretentious. I said, well, you're coming up with it. I just happen to have the same name, but I don't care because it wouldn't be not named after me. But I mean, yeah. What you're saying basically is that because we are introducing a new level, and we're giving a model to this stuff. No, we are no longer in this problem of this ambiguous, what is mass and how do you measure it? Because you measure mass by the level below it.
Yes.
Right?
Exactly.
And it doesn't matter what level in the universe you're at.
They're using, in that film, that lady's using level 2 gravity to make this G1 flow go in a circle, and yet they go back to kilograms because they interrelate the electrical energy with the mechanical energy, and they say energy is equivalent to energy is equivalent to energy. And then they can pull in the kilograms to go with it. To me, it's amazing. They're doing it right. And they come up with what I consider...
Because they don't have the reason is, and it comes down to the same thing over and over, which our model does. We give it physicality. And when you give all the universe physicality, you no longer have ambiguous things like, oh, the universe is electric only, or oh, the universe is only gravity, or oh, this is an electromagnetic field, and this is a magnetic field. All of those things now become unambiguous. Well, yeah, they can actually be, one thing they sort of can live together, but the thing is how we define them. We can define them. For instance, is at the level where we have all the planets going around the sun, is that magnetic? It is at that level.
So one more comment to all of the stuff I've been ranting about is that if you're going to measure the G1 particle with a G2 gravity, you have to have a G2 gravity scale.
Yeah.
We don't have one. There isn't any. No, and there's no standard for G2
So
mass.
Whoever's out there and builds one, name it after my dad. Because you have Newton's got his force.
Well, yeah, but did Newton name it after himself?
He didn't. That's what I'm saying. So I'm just giving everybody a hint. That's what you should do. Name it after him. Anyways, like I said, our model is either going to give us fame or infamy, or not neither, or it'll be. But we actually think it's pretty amazing. So. I guess we've gone 40 minutes already. We need to discuss, but I think we're good. We don't want to go on and on every day. But so what are you planning on tomorrow? We're going to be talking, I guess one of the things we'll talk about is where we put the Wang. And I think...
Well, I'm going to go ahead and write it, but wherever, it doesn't matter where, I can move it.
I think what we do want to do, and this is just again, this is why we're doing this, is to show people how we're right, how the book is going. That we should explain it, because one of the things our model should do is explain phenomenon.
Which one are you talking about?
Wang, Wang.
Yeah.
So we can explain
Well,
that, and you don't have verse hack. But if we want to get into real details,
it's going to be even to explain it. It takes we'll see what it takes.
I'll make a picture for it, and the picture's worth 1,000 words, and then we could even throw out everything
I thought mine was.
In fact, we
beautiful.
could make this the Principia Mathematica 2, a comic book with only pictures. So there you go.
Oh, wait a minute.
All right. Farouk did ask about consciousness, but I referred him to George Coyne. He was at one of our conferences and talked about that, and it's more of an analogy to computers, the head and stuff. So We don't talk about that, Farouk. We're sticking basically. We're not doing anything like UFOs or infinite energy or anything like that. We figure giving physicality to light and gravity and magnetism, electricity, and then being able to explain a bunch of stuff like the double slit experiment that no one else can explain, and all kinds of other things is quite enough. So we're sort of trying to stay to that.
But we do have a section in biology which does get into the human body and how this,
oh yeah, we do that. But that's not like,
well, that's not exactly his question. All I'm saying is that's as far as we've gone in that direction.
Yeah, my dad's actually looked a lot at that, and that's sort of related to consciousness, but in some sense it's the body and how we perceive, and that is
But
how
I don't get into the brain per se.
yeah, we don't get into the brain part, but what we do get into is how our model, which is modeling light, actually works in the eyeball, and why we see white versus other colors, etc. And that's also going to be in our book, and that's probably going to be one of the harder parts that we're going to get to. I'm doing all the easy parts right now, but so tomorrow I'm going to continue on charging through the book from the top down is what I'm doing, finding places where it needs to be filled in, and then there's.
I'll probably work on. I can still do Lesage. Newton and Lesage as they're tied together in terms of gravity.
Okay. Alrighty. And again, please subscribe to our YouTube channel. And if you do, you will, in fact, be able to see some chats that we have during the day. Which way we sit down right here. I stream live just to YouTube, to an unlisted video, and then you get to see some pretty heated arguments sometimes. And so please subscribe. I think we're already at 25. I mean, it doesn't sound like a lot, but that's pretty good for a short amount of time. And we hope to see you here every day. Again, we're going to be working on it every day. So if we get a chance, if there's a day we can't get it because, I know Sunday we're going to be busy, and then we have people over, but I think we probably can get something in there, but we're going to try to do it every day. But if not, we will announce it and try to announce it a little more ahead of time with our schedules, because when we announce it, people can plan to be here instead of just showing up. So I want to thank you guys for showing up and asking questions. I see three or four people here that have made some comments, so that's greatly appreciated. So that's it for today, and it's going real well. And like I said, those interested in buying the book, what we're going to do is when we get to a point where the book, we have a good idea of pretty much the page count, we're going to go to Lulu, we're going to create one, send it to ourselves, take a look at it, make sure it's looking pretty good. We're going to have a ballpark figure on it. We'll add a couple more dollars to it. And then we're going to order a bunch of books, maybe 25 to 50 books on our own. We'll pay for them, and then people who order them ahead of time and pay for the book and the shipping, you're going to get a better price, because of course Amazon will jack those prices up. And we will sign them if you want to have something in it, or we just say hello, sign them and send them to you. We're hoping to do that at the beginning of fall, September time frame or something like that. So we're working like crazy. I'm on vacation time now. Well, today was a paid holiday, but I'm on vacation all next week, so going forward. Alrighty. Appreciate it, everybody. Take care and subscribe and like. See you tomorrow.
Bye.